All right, welcome to another SciAps video. Thank you very much for tuning in. We have some really exciting news today. It's called carbon. So for the first time, we have a handheld analyzer, the LIBS unit, that can analyze carbon in the field in a matter of 10, 20 seconds, depending on what you're actually trying to accomplish. So we've been working on this for quite a while, and we really are now ready to release our first carbon testing app. So it's big news, and I'm here today with Brendan Connors. Brendan is a senior scientist here at SciAps, and he's the developer of this app. He's been doing a lot of great work on it, and I felt because of that, we're going to have him come and do the video and show you guys how it works. And besides, what we call Brendan around here is the Bill Gates of handheld libs. So we figure we got to have him doing the video. All right, Brendan, take it away.
All right, so we're using a handheld LIBS analyzer to analyze carbon in carbon steels. Now carbon, the main emission line we use is at 193 nanometers, so it's pretty far into the UV. So for all kinds of OES spectroscopy, you really need to use an argon purge if you're going down into the UV. So the Z200, the SciAps Z200 uses an internal argon purge to do our carbon analysis. And so...
Can you show it? Can you flip the door and show it?
Yeah, so we have a little argon cartridge in the handle of the analyzer, and it just purges the nose area right here, right where the laser spark happens, right where the sample is. And so LIBS uses a laser to vaporize a small amount of the sample, produce a plasma, and look at the emission from the elements that are in the plasma. And so because we're using a laser, we can use that to clean the sample too, so we can get rid of some small amount of surface contamination if there is any on the metals, on the alloys that you're testing. So for testing carbon, we usually do an average of a couple of results just to make sure you can improve your precision as much as possible. So I have a 4130 sample here, so I'll just test this a few times and we'll see the carbon value. So 4130 has about 0.3% carbon. So the analyzer is going to prompt me to test a few repeats. And so what the analyzer is doing is it's actually looking at each spectrum that comes in, and it's doing some data rejection in case there happens to be any outliers, or you happen to hit a spot that has some surface contamination. And so it's applying some statistical analysis to basically to all of the data that come in to make sure that you're only getting the most repeatable data for your carbon result. And so here we have the sample has 0.3% carbon, so we're getting a reading of 0.26 plus or minus 0.04, so that 0.3 is right within that spec.
Let's see. So the software requires at least 3, usually maybe 4 to 5 tests to average, good tests, right? And we'll explain what a good test means a little later. But so does the operator, he pulls the trigger 3 or 4 times, and then the software automatically averages each test, is that right?
Yeah, so okay. The software, so when you start a test, the software is going to prompt you to test a certain number of times, and that's user settable, but it's usually a minimum of 3 or 5 tests. So every trigger, so you do have to pull the trigger each time, and we recommend testing a different location each time, but the software is going to keep count of those, and it's only going to report a carbon result after you've hit that minimum number of tests. So we hit 1, run another one, and I have it set to a minimum of 3 good tests. Okay, it's prompting me for one more.
Oh, so it sensed a bad test.
It did, yeah.
Okay.
It saw a bad test, and it rejected it.
All right. And there's your 4130. All right, very good. And you got 0.3 carbon last time and 0.27 this time.
We got 0.26 last time.
0.27
this time.
God, that's even better.
All right, so I have a 1018 that has, this one actually has 0.17% carbon in it, so we'll shoot this a few times and see what we get for a carbon result.
Oh, look at that. It's like a perfect match to a 1018.18 carbon. Beautiful. So I see that there's the carbon equivalence. We're also showing carbon equivalence in this software, which is also unique. Nobody does that with a handheld either. You want to tell me a little bit? Can you tell me a little bit about the carbon equivalence?
Sure. So we're calculating the carbon equivalence based on the results for a few other elements. So even though this is carbon mode, we're doing a full elemental analysis of all the other elements that commonly show up in low alloy steel. So we're also looking at silicon, manganese, nickel, copper, moly, and vanadium. And so we use all of those to plug into the carbon equivalence formula to report total carbon equivalence reading. We'll calculate that carbon equivalence value, but if one of those elements that gets plugged into the formula is a non-detect, like in this case vanadium is, we'll just put a less than sign in front of the carbon equivalence just to show you that it's that's the maximum that we would expect for a carbon equivalence value. The real value might be less than that.
Yeah, that's great. And this uses the standard Dearden O'Neill, the IIW formula for carbon equivalence, right?
Yes.
All right. So tell me about, Brennan. I know we talked about how important grinding is for measuring carbon. Can you tell us a little bit about what you've learned and like what you recommend, what we recommend for grinding? Thanks.
So you can use laser cleaning from the LIBS analyzer to remove small amounts of surface contamination, but for carbon contamination on the surface can be really tricky to remove. And so in addition to the laser cleaning, we usually recommend grinding the sample surface before you test. And that's really it's probably the most important thing you can do to get accurate, repeatable results with the LIBS analyzer for carbon. So for grinding, there are a couple different options available. We've been using a handheld grinder with a ceramic grinding wheel on the front, and just grinding just for a few seconds, sometimes a little more depending on if you have an oxide or scale layer on a sample, just to get rid of the any surface contamination and get down to a shiny surface so you can test it with LIBS.
And so when the software rejects a reading, we think that's generally because it hasn't been properly ground and you still got high carbon contaminant on the surface.
Yeah,
Did you say that?
Yeah, that's one of the reasons that the software can reject a result or reject a particular test location. Can also be due to surface inhomogeneity or sample inhomogeneity if you hit an inclusion, but improper grinding of the surface is probably one of the biggest reasons that you would trigger the data rejection in the software.
The calibration range on this, roughly 0 to sort of 1% carbon or so?
Yeah, that's about there. I mean, we think that most of the interest is going to be in separating 1018 from the 1000 series, 1018, 1030, 1050, 4130, 4150, but we go up to about 1%.
Yeah, got it.
All right, so yes, we're testing at 1050, coming out has 0.5%. We're coming out about 0.48%.
Very good. A lot of our testing hasn't been just on nice, CRMs. We've been working with a major refiner who's given us some previously in-service piping components, which we've ground and shot, and that's what I put in front of you. So, just as an example, maybe just grab any one and give it a quick grind for us and shoot it and see how it looks.
Okay, sure. Yeah, so the CRM samples, we use those because we know what the carbon content is of them, and for a lot of other user samples we don't. But these are for pipe samples that had carbon content and other elements verified by OES, Spark OES, and so I'll just do a quick grind on one of them. I've already ground a couple spots on the surface, but I'll just do a quick grind and test it for carbon. So yeah, depending on how much scale layer or oxide, you may only need a few seconds of grinding. And Analyzer has a camera on it that's really helpful for positioning to find out, make sure exactly that you hit exactly where you ground the sample.
So there's your 836.
Yeah, so it's reporting 0.24%.
Yeah, pretty good. All right. Very good, very good. Hey, can you scroll down? I'm curious why why the carbon equivalence is a less than. What was not detected? Again, really low vanadium. All right.
Yeah.
And low chrome, I see. Got it. Okay.
Yeah, actually, yeah, nickel and copper too.
Yeah, you're right. Not much. All right. Okay. All right, Brendan. Thanks a lot for doing that. So, you're younger, smarter, and better looking, so it looks like you'll be doing the videos from now on.
I don't know about that.
Yeah. So let's see. I think a couple key points are, unlike a lot of other alloy testing, a little bit of care and carefulness has to go into carbon testing. Would you agree with that?
Yeah, definitely. It's a lot harder than most of the other applications that we do. A lot of the other elements that we look at. It's the surface contamination that you have to watch out for.
Yeah. And QC wise, what would you think? I mean, because it's not really just point and shoot. Like you said, you got to grind. You got to make sure you're taking good tests. I like the fact that when you could do these curved surfaces, right? Because libs has to be flush to the material. So that was good to see, and that we handle that. What kind of QC are we talking? Like do you drift correct daily, or what do you think?
You definitely want to have check samples on hand so that you're testing, say, a blank, a low, and a high compared to what your testing range that you want to look at is. Running 3 drift correction samples or 3 check samples daily would be a good idea. As far as drift correction goes, it's something you may want to do, say, weekly or slightly less often than that. It's not something that we've seen you have to do daily.
Right.
But you'll want to develop your own. Requirements to make sure that the precision that you're getting, that you're doing enough averaging to hit the precision that you want, and that if accuracy is a concern, particularly if you're trying to separate do a tight separation like 4130 from 4140,
right.
Just make sure that your accuracy is really good so that you're able to do that reliably.
You can do that in the software. You can go in and just use a subtype type of curve, not tight calibration, but maybe just pick out the 4100s and some other alloys that are similar, and just have more of a matrix type calibration.
Yep. Yeah. So you can. The software lets you do the drift corrections as well as do type calibration to a particular sample, or you can set up a calibration curve that's only for the samples of interest. So if it's only 4000 series that you're looking at,
right.
You can set up a calibration curve for just the 4000s. In practice, you're not really seeing a huge amount of matrix variation within the carbon steels and the really low alloy steels, but the more targeted your calibration is, the better your accuracy is going to be.
All right, I got to ask, what about L grades?
L grades require separation below 0.1%, so like 0.04 to 0.08. So that's our detection limit for carbon's about 0.1, maybe a little 0.1%. So that's too high to do L grades. So we can't do L grades.
No more videos.
We're working. We're working on it. Yeah. Okay.
No,
we can do it. We can redo it.
No, in all seriousness. Yeah, that's something that we hope to do it someday, right? But it's just not there yet.
Right.
All right. Are we both in the video? Are we both in the fixture now?
Yeah.
All right.
You're rolling.
All right, you ready?
Okay.
God,
yeah.
you really did a great job on this, Brendan.
Yeah, so it's
All right. Man, good-looking movie star and smart.
Brad Pitt.
That's right.
You just got to get your hair kind of disheveled.
I'm not sure if I can get 50% of that. But.
Yeah. Well, plus you got all those kids too.
Well done.
All right.